In the previous video, we had learned, or in the previous section, we had studied about two major new concepts that had come in, called as de Broglie's uh, dual nature of matter, as well as Heisenberg's uncertainty principle. Till that point in time, there was something called as classical mechanics. So classical mechanics was based on Newton's laws. That is, if you remember, you would have learned it in physics, three laws of motion. And this was successful for explanation of movement of various macroscopic particles. As we know, microscopic particles, they started showing different things, like they acted as both particles as well as waves. And the issue with classical mechanics was the fact that they did not consider the wave-like nature of particles. So it was only considered that particles exist and they move as, they are particles and they cannot move as waves. However, electrons, on the other hand, show both particle as well as wave-like nature. And that's when a new branch of science started, that is quantum mechanics. So one important thing is that it's a theoretical science and it is to do with the study of motion of microscopic particles, which have both particle as well as wave-like nature. One interesting thing is that when this quantum mechanics is applied to macroscopic objects, that is, for normal objects around us, the results were the same as that were for classical mechanics. So quantum mechanics was developed independently by two scientists, Werner Heisenberg as well as Erwin Schrödinger. So it was here, the whole quantum mechanics thing requires a lot of mathematical abilities and skills, and the equations in quantum mechanics are quite complex. So for now, we will be learning all of this like as a base. We'll try and get a basic idea behind all of this. And the fundamental equation for quantum mechanics was developed by Erwin Schrödinger, and he won a Nobel Prize in Physics in the year 1933. So the equation he had given, the equation incorporated the wave-particle duality of matter, which was proposed by de Broglie, and it was quite complex. So we'll not be looking into all of that. But for a system such as an atom or a molecule whose energy does not change with time, Schrodinger's equation is written as H cap psi equals to E psi. So the H is the mathematical operator, which is also called as the Hamiltonian operator. This basically gave an idea as to for us to calculate the total energy, which includes all the kinetic energies of the subatomic particles and the attractive as well as the repulsive potential amongst the electrons. So attractive would be between the electrons and the protons, repulsive between the electrons, and the solution of this particular equation will give us E and phi. So for now, we will just be understanding all these concepts theoretically, and like as you go into chemistry, as you complete your bachelor's and master's in chemistry, then you'll be learning about all these equations in detail, and maybe that time you'll be able to appreciate it even more. So in this video, we had learned about the introduction, that is the quantum mechanical model of the atom, which was basically a solution to all the issues faced by Bohr's model. So according to classical mechanics, the reason it couldn't work for microscopic particles is because it did not consider the wave-like nature. So quantum mechanics came in, and which considered the wave as well as the particle nature of the objects. In the next video, we will be discussing about the hydrogen atom and Schrodinger's equation. So do check it out.